And welcome back. So we're talking about galaxies and how they come in different shapes and sizes, and how we need to sort of try to make sense of this morphology and organize them in some way. Somebody you may have heard of called Edwin Hubble did this in the early 1900s and made his famous Hubble tuning fork diagram. And the Hubble tuning fork diagram works like this. You have the elliptical galaxies on the left. These are early type galaxies now known as, and the spiral galaxies are on the right, late type galaxies. And in fact, you can even break these down into different types, right? These zeros, the zero refers to how elongated the ellipse is, sort of an eccentricity of the ellipse. Zero being a perfect circle, up to E5 and even E7, these are getting more and more elliptical, more and more elongated, more and more eccentric, the orbits, or the shapes of these galaxies. Then you've got a sort of transition, the lenticulars. These S0 galaxies and SB galaxies are the transition between the ellipticals and the spirals. And then you've got these spirals forming two arms, the non-barred spirals on the top and the barred spirals on the bottom. And these two are broken down into categories. So SA, SB, and SC galaxies. SA galaxies, you can see here, tend to have larger bulges, tend to have tighter spiral arms. And as you go to SC galaxies, the bulges are very small now, and the spiral arms are very loose spiral arms. Same with the SB. This gets confusing because a capital B here means a barred galaxy, as opposed to a lowercase b, which indicates that it's between an SA and an SC galaxy. But your SB galaxies can also come in A, B, and C from very large central bulges and very tightly wound spiral arms to very small central bulges and very loosely bound spiral arms. If you were to put the irregulars on the diagram, they would just sort of be off here to the right on their own, doing their own thing. Now, when Hubble put this together, you can see why it's a tuning fork, right? You've got the handle of the tuning fork here, and then the two forks of the fork come across as the two branches for the barred and non-spiral spiral galaxies. When Hubble first put this diagram together, he envisioned this as an evolutionary diagram. You can sort of see how the thought process works. Galaxies begin life as a large ball of gas. That gas slowly contracts onto itself and forms a disk. And so as you go from E0 to E5, you can see that disk slowly coming together. You enter an evolutionary stage intermediate between as the disk is forming, and eventually you form these tight spiral arms with a big central bulge. That central bulge slowly goes away, and the spiral arms become less and less tightly wound, and eventually you end up down here as an irregular galaxy. It was a nice thought. It's completely wrong. And we've already seen some reasons why it has to be wrong. I'll let you think about it in a second. So let me ask you, what evidence have we already seen that this probably can't be the case? Well, one thing is, where are the young stars? They're only being formed in these spiral galaxies. These blue colors indicate youth, right? These elliptical galaxies only have old stars. How is it that old stars can evolve into young stars? Well, they can't. We know now that this is not an evolutionary diagram at all. It's useful for still used and useful for categorizing the morphologies of galaxies, but it's not in any way a morphology of galaxies. If anything, spiral galaxies can turn into elliptical galaxies through merger events and things like that. Some other differences between elliptical and spiral galaxies is that spiral galaxies tend to be found more prevalently in small groups, isolated or up to a few dozen galaxies. Spiral galaxies are more dominant. And elliptical galaxies are far more prevalent in huge clusters of galaxies, hundreds of to thousands of galaxies, like this gigantic cluster of galaxies. You can see many more elliptical galaxies in this view than spiral galaxies. And this leads credence to the fact, to this hypothesis that you can form elliptical galaxies by merging spiral galaxies together. because mergers are much more likely to happen in a high density, galactic density environment like this than they are in a low galactic density environment. Okay, but we need to talk a little bit about some history. So let's go back to the early 1920s when Hubble was doing his thing. We didn't even really at that point understand what galaxies were. And I mean that in a very, very specific sense. There was, in fact, a great debate that occurred in the year 1920 between two very prominent professional astronomers, Harlow Shapley and Heber Curtis. And this actually was a debate. It took place at the Smithsonian Museum of Natural History, and it put two worldviews of the universe against one another and highlighted the fact that we had no idea really what the universe was, how big the universe was, or what these spiral galaxies were. And the issue stemmed from the fact that we had no idea how far away these were. So Harlow Shapley argued that these spiral nebulae, as he referred to them, or they were referred to at the time, were part of our own galaxy, right? And the sun was not at the center of our own galaxy. So Harlow Shapley had actually, I don't know if you remember back to our Milky Way talk, was the one who had discovered the distances to globular clusters could be measured and found that we were not, in fact, at the center of our own galaxy. He was right about that. He was wrong about this. Again, we had no way to measure the distances to these things. He thought that these were objects within our own galaxy and that the Milky Way galaxy was the universe and there wasn't anything bigger than it. Curtis, on the other hand, argued that these spiral nebulae are, in fact, other galaxies just like the Milky Way, much further away. He also argued that the sun is at the center. So Harlow Shapley turned out to be right about the sun's position in our galaxy, but not about these spiral nebulae. And Heber Curtis was vice versa. Anyway, nobody really won this debate because at play was we had no idea how far away these galaxies were. Were they, in fact, located within our own galaxy, or were they, in fact, so big and distant that they could be as big as our own galaxy? Again, this has profound implications for how big the universe is. This is not a small question. It's a very important question to answer. And until we can determine how far away these things are, we have no idea what the answer is. So let's talk briefly about how we measure distances in astronomy. I mentioned when we were still having class together in the early part of the semester that this was a very important aspect in astronomy and very difficult. And this is where it starts to rear its head. So this is a nice diagram that tells, sort of shows the scales over which we can use different methods to find differences, to find distances to things. We have already talked about a couple of these methods. We have talked about parallax. Remember, the Earth is orbiting the sun, and we can use the fact that we have two vantage points to make it so that nearby stars actually appear to move on the sky as the Earth moves around the sun. And for nearby stars, we can actually use parallax to get actual physical distances. Within our solar system, we can use radar. You can just send a radio signal out. It will bounce off an object like the moon or Venus, and you can time how long it takes for that signal to come back. And again, use straight geometry and the speed of light to determine distances in our solar system. So we have nice, robust ways of getting out to about 1,000 light years or so with parallax. Beyond that, we've also seen main sequence fitting, right? We didn't do this lab. We would have done this lab just after spring break, but you can use main sequence fitting. The fact we did talk about how you can determine which of these clusters is closer to us by, for instance, which one appears brighter in the sky, right? So we know that these two stars, for instance, in the Pleiades and the Hyades, have the same surface temperature and therefore probably are the same mass on the main sequence and therefore have the same luminosity. And we can show that since these Hyades stars appear brighter, they must be closer to us. And if we know, for instance, where the sun is on this diagram, and we know the brightness of the sun, we can use this to calibrate the scale and actually determine the distances to all of these clusters by main sequence fitting. The rest of these, but that again only gets you out to about the edge of the Milky Way galaxy. We're not making these diagrams for clusters and other galaxies. At least not very, we weren't in the 1920s, that's for sure. So we need some other method, right? So how does this work? Well, we use parallax and radar to determine distances to nearby things, from which we can calibrate these stars and then use these stars in main sequence fitting to determine distances to other things. We're using, in this case, the method of standard candles. So that's the most common way of measuring the distances to things. Let's talk a little bit about how standard candles and standard rods work, right? Standard candles are the fact that if we know an object's intrinsic brightness, its luminosity, if we know how much energy it's giving away, we can use the fact that we know how much fainter an object will get as it gets further away from us to determine. Remember, we wrote down a formula at the very beginning of class when we're talking about light, which related a star's luminosity or an object's luminosity, its size, its distance, and its distance to us, right? If we know an object's total luminosity and we know its brightness, we can determine the distance. And those three things are related. And if we know any two of them, we can get the third one. And so if we happen to know, let's say there's an object whose brightness, intrinsic luminosity we know for other reasons, we can always measure its apparent brightness, and that will give us the distance to the star. That is the method of standard candles. The method of standard rods is also shown on this diagram. If you know that, say, for instance, all spiral galaxies have about the same size, then you can use its apparent size to determine the distance to the star, to the galaxy. How big it actually appears in the sky will go down in a very regular way as the thing gets further and further away. So this is the method of standard rods and standard candles, both of which can be used to measure the distances to things. So let's talk about some of these standard candles. What could we use to actually determine the distance to a star? What objects are there out there that we know the brightness of? Well, this is an important one, Cepheid variables. These are, there's a region in the HR diagram that we haven't talked about mostly in the giant branch, giant part of the diagram, that is the instability strip. And stars that are in this strip are pulsationally unstable. What does that mean? It means they are physically pulsating in and out. Unlike we don't call these things pulsars. Pulsars are not pulsating in and out, but there are stars that pulsate in and out, and they happen to be on this instability strip. The ones at the top of this strip we call Cepheid variables. The ones at the bottom of the strip we call our Lyra variables. It doesn't really matter. It's the same phenomenon. They were just discovered slightly independently, and these are specifically the kinds of the names of the stars. Cepheus is a constellation, but there was a star in Cepheus, and our Lyra is a variable star that formed the archetype of these particular stars. But the important point is they're all really the same thing. These are pulsationally unstable stars that are pulsating in and out. Now, that in itself isn't all that useful, although it is useful that these Cepheid variables are extremely luminous and can be seen at rather far distances, even in distant galaxies. What makes these things useful is there's a relationship between where they are in the strip and how long it takes them to do one of these pulsations. So let's take a look at this interactive figure. Oops. Okay, I'm not actually going to show the interactive figure, but it doesn't really matter. It's just going to be showing this thing as we go along. The idea is, so these things are odd, right? They get bigger and they get smaller, and they get bigger and they get smaller. And the temperature changes a little bit too, but in general, when a star gets bigger, it is more luminous because of that luminosity equation, L equals 4 pi r squared sigma 2 to the 4th. So as the radius increases, the brightness, the luminosity of this star goes up. And therefore the brightness goes up because the distance isn't changing. And so if you watch this thing over several days, it will go through a cycle of being big and bright, and then going back, shrinking back down again and getting cool again, and getting faint again. And it will repeat this as often as you want to, as long as you want to observe it. Now, the interesting thing is that the period of this pulsation, how long it takes to go from trough to trough or peak to peak, is a function of, a linear function of, how luminous the star is at its brightest point, right? And so this is a very useful thing, right? How does this work? Well, the more luminous a star is, the bigger it physically is, and the longer it takes to go through this physical cycle. That's the why. But it's not even really important why. as long as you can get enough of them that are close by, let's say close enough to get parallax measurements for, or in clusters whose distances you've measured, you can know the luminosities of these stars because you know the distance and calibrate this scale. And then you can use these things as standard candles. If you can measure the period, and the measuring the periods is easy, is all you have to do is watch these things vary over several days, over several cycles, and then figure out how long it takes to go from peak to peak. You can use this chart to tell you what the absolute luminosity of the star is. And once you know what the absolute luminosity, it's a standard candle, and all you have to do is measure the brightness to get the distance to it. So that's the method of standard candles and how it works, particularly with Cepheid variables and the very important period luminosity relationship. You can measure the period easily, that tells you the luminosity, and you can use the luminosity to tell you the distance to the star. Okay, so we're going to come back to this. This is very important when we're talking about measuring properties of the universe. I'm going to briefly take an aside and talk about spiral arms, though, before we move on to that very important thing. So stay tuned for the next video about spiral arms. It's going to be great.